We will analyze some systems where we will have to find out the total torque acting on a system. So let us look at some examples of how to find out net torque. Net torque is the sum of all torques acting on an object. And if an object is in equilibrium, meaning it is at rest or it is rotating at constant speed, then the object would have net torque of zero. So in equilibrium, net torque is zero. It is similar to equilibrium situation when net force is zero. A red pencil is being balanced here. At the middle, there are two coins attached to the opposite ends of the pencil. Let us see how we will write the net torque expression for this situation. Because the system is balanced, we know it is in equilibrium and the net torque would be zero. Symbolically, how would we write the torques produced by the two forces here? Let's look at this coin. Its weight is Fg1 and its distance from the center is R1. So the torque produced by this coin would be Fg1 times R1. And because its sense of rotation is counterclockwise, so it would be positive. The torque produced by this coin on the right would be its force, which is Fg2 times its distance from the center, which is R2. And because this torque is clockwise, it would be considered as negative. So this torque would be Fg2 times R2. And this is how we report the net torques. Tau1 minus tau2. We are going to solve a few problems in this video. First problem, find net torque about point P. We have got a rectangular object that is pivoted at this point P and three forces acting on this object, 20 Newton, 15 and 5. And we have to find out the net torque by these forces at the point P. Let's review the formula for torque. Tau equals perpendicular force times the lever arm. We notice that all of these three forces are perpendicular to this rectangular object, so we do not need to break any of these forces into components. The lever arm for 15 Newton is 0.25, for 20 Newton it's 0.15, and for 5 Newton it is the sum of 0.2 and 0.15. So it would be 0.35 meters. Let's also check whether the torques produced by these forces are clockwise or counterclockwise. So 20 Newton tends to rotate the object around pivot in this direction, so it is clockwise. Same thing for 5 Newton, that is also clockwise, and 15 Newton tends to rotate it this way, so it would be counterclockwise. Let us write the net torque for all these three forces. We can write sigma tau. Sigma means adding up all the torques. For 20 Newton, it would be negative because it's a clockwise torque. Negative 20 times 0.15. Negative for 5 Newton as well. So minus 5 times 0.35. And positive for 15 Newton. 15 times 0.25. We calculate it to find a final value of negative 1 Newton meters. So as a result of these three forces, the object will rotate clockwise. Next problem, we have to obtain an expression of net torque acting on this system. This is a rectangular object pivoted around point O. So we have to find out sigma tau, sum of all the torques acting on it as it is pivoted at point O. There are three forces, F1, F2 and F3. First thing to notice is that F3 passes through the pivot or axis of rotation, so its lever arm is 0, so the torque that it will produce will be 0. The second thing to notice is that F1 and F2 are not perpendicular to this line, which means that we have to break them into components, and only the components which are perpendicular to this rectangle will produce torque. Let's draw these components. For F1, F1 sine theta produces torque, and for F2, F2 cosine phi produces torque. Let us label the length of this rectangle as L. So sigma tau, the torque by F1 would be F1 sine of theta times the lever arm, which is L. And because F1 sine theta tends to rotate it clockwise, I will put a negative sign. For F2, it would be the component which is perpendicular. So F2 cosine of phi times the lever arm. Lever arm in this case is half of the length. So L over 2. Because this will tend to rotate it counterclockwise, I will put a positive sign here. There is no torque by F3, so that's the final expression. This is an experimental setup which is used to study torques. The meter stick can be balanced around 50 centimeters and two masses are hung on the opposite sides. If the two masses are equal, then their distance from the pivot would be equal in order to produce equal torques in opposite directions. But if one of the mass is heavier, it should be put closer to the pivot because its force would be bigger, which means the lever arm has to be smaller in order to produce an equal and compensating torque. The question is, how can you use this setup to find an unknown mass? For example, if this mass is known, you know its value, but there is another mass which you do not know. How will you find out the unknown mass by using this setup? I leave this question to you. You may pause the video and write its answer in your notes.